Hey everyone, Schelling model shows how the effect of homophily that operates at a local level leads to some interesting global patterns in the network. In this video, we're going to implement this model and we'll observe the patterns that emerge. Before we start the implementation, I'll give you a brief of the model. Let's assume that there is a population of people and these people are one of the two types. That is, every person is either of type 0 or type 1. Further assume that these people live in a city which is like a grid. That is, there are cells in this grid where these people live, just like this. Also, some cells of this grid have people, whereas some cells will be empty. In other words, every cell will either have a person of type 0 or a person of type 1, or it will be empty. For example, like this, as you can see, every cell either has a red node, or you can say red person, or a green person, or it is empty. Correct? Now, a cell's neighbors are the cells that touch it, including the diagonal cells. So you can imagine that a cell that is not on the boundary will have 8 neighbors. For example, if you look at this scenario, this red node is an internal node that is not on the boundary. So every node which is not on the boundary will have 8 neighbors like this. The red person has basically the cell that has red person has 8 cells which are its neighboring cells. Similarly, if you look at the boundary cells, there can be two cases. First case could be where the cell is a corner cell, like here. The red person is staying in a cell which is a corner cell. So this cell has 3 neighbors, as you can see here. The other kinds of boundary cells can be like this, which are not the corners. So as you can see, this red person which is residing in this cell has 5 neighbors. I think it's not difficult to understand that we can convert this whole scenario into a graph where the cells are the nodes and there is an edge between two cells if they are neighbors on this grid. So that's what we are going to do. We are going to analyze this grid using a network. Now, if you look at a metropolitan city where there are people from different states of the country, everyone tends to, or rather prefers to, stay in an area where there are more people from their own state. So that practically happens. We are going to apply the same scenario in our given grid. So the people in our model wish to have at least some other people of their own type as neighbors. Now, as an analogy, if you look at a metropolitan city, for example, where there are people from different states of the country, everyone tends to, or rather prefers to, stay in an area where there are more people from their own state. In a similar fashion, the people in our model wish to have at least some other people of their own type as neighbors. So what we'll do is, we'll assume a common threshold T for each person. If a person discovers that it is surrounded by fewer than T people of its own type, he tends to move to a new cell. Such a person is called unsatisfied with his current location. As an example, if we set the threshold T to be 3 for instance, and if you look at this node labeled 1, it has 8 neighbors, as you can see, and out of these 8 neighbors, 4 neighbors are of its own type and the rest 4 neighbors are of different types. So since the threshold is 3, it has more than 3 neighbors of its own type. So we will call this node 1 to be a satisfied node. If you look at the other scenario, for example, if you look at this node labeled 1, it's of green type and it has 8 neighbors. Out of these 8 neighbors, 4 neighbors are of the different type and 4 neighbors are of the same type as the node 1. Now, since as an example, if we set the threshold T to be equal to 3, let's say, and we look at the node which is labeled 1 here, as you can see, there are 8 neighbors, and out of the 8 neighbors, 4 neighbors are of different type and 4 neighbors are of the same type as the given node 1. Since the threshold t is equal to 3 and this node 1 has more than 3 neighbors of its own type, we will call this node 1 to be a satisfied node, right? And if we take one more example, and if you look at this node which is labeled 2 here, it again has 8 neighbors. Out of these 8 neighbors, 6 neighbors are of different types and 2 neighbors are of the same type as the node 2. And the threshold t we have set to be 3. Since this node 2 has lesser than t neighbors of its own type, this node 2 will be called an unsatisfied node. Now, as I already explained, the unsatisfied nodes tend to move to new locations which are already empty and where they are likely to be satisfied. There are different versions of Schelling model in this context. For example, in some of the versions, the unsatisfied nodes will move to those locations where they are more likely to become satisfied. Or in other versions, the unsatisfied nodes will move to any random location. So there are different versions which you can implement. Another thing is that whenever a node moves from one cell to the other cell, it affects other neighboring nodes as well. For example, in this process, some other nodes might become satisfied, some other nodes might become unsatisfied. So it basically changes the scenario of the cell of the grid, right? So in every iteration, we choose some unsatisfied nodes and we move them to new locations, and the cell and the grid structure changes, and this keeps on repeating, and we can analyze the structure that we get in the end, that is after a certain number of iterations. So this is what we are going to implement. We are going to implement the version of Schelling model where the unsatisfied nodes move to the random locations, and we are going to run several iterations of this process. We are basically going to recalculate the unsatisfied nodes in every iteration, because that is obviously required, because one shifting affects the rest of the nodes as well. So let's get started with the implementation now.